In this video, we are going to talk about the insulation and roofing, and we are going to cover these subjects. First, we are going to start with the functions of the components, then the water insulation and heat insulation, roofing products, drainage systems, and the last subject is the flat roofs. Let's start with this question. How do different components help with the function of the roof? I think you remember this example. It's the ecological living module, a tiny house which is designed for its user to live a life without depending on the outdoor sources, let's say. Here we can see that the roof, it helps with the producing of electricity, and it collects rainwater. Also, there is this wall which you can grow edible plants. There is this entrance terrace, a tiny terrace. At the back, we have this system to recycle the used water, gray water. Inside, we see that there is the sofa, a dining table, a small kitchen where you can prepare your food, and behind this wall there's this shower area and the toilet part. Here you can sleep, and you remember that we can use this hierarchical product building product system in order to make proper decisions during the architectural design process. We can start with the building, and first we can make mass decisions. We can design the building as its geometrical shape, the colors, its external appearance, and the location of the mass, the position and relationship with the near surrounding. Once we create this envelope, we know that it will include different units. These can be closed living spaces, semi-open living spaces like this terrace area, or open areas, which is related with this envelope. And each one of these can serve for a specific function, such as sleeping or preparing food or eating food. The main function of the envelope is to protect the user from all the negative features in the outdoor environment, including that main function and these specific functions. Each of these functions will be executed by building elements. Elements such as this wall here or roof, and that's the definition of a building element. These are integral products which can be formed to physically meet one or some of the functions of the building, such as sleeping, preparing food, or eating food, or to be protected from all the negative features. All these functions of the building element, one of the building elements, can be executed by its components, such as this wall. It can have different components, different layers, or this roof here. That's the roof. Let's imagine that that's the building that we designed, and this is the roof part. And there needs to be different components. We need to first create these components, and when we gather them all together, we will have the element, the roof element. And one of the functions that these components need to provide is to keep the form intact. And in order to do that, we need one of its components, this structure component. That's different from the building structure. It's the structure of this element here. Let's imagine this is the indoor area where the user will be. And based on the climatic conditions or geographical location, the outdoor environment may get cold. And we need to keep the indoors at a certain temperature level for the sake of the user, to provide a comfortable and healthy indoor environment. We know that the heat always transfers from the hot area towards the cold area. And if we want to stop this or slow this transfer down, it's not just related with the roof, obviously. We are talking about the whole building envelope, and specifically for the roof, we need to keep the heat inside, or based on the climatical conditions or geographical location. If you are living in a hot area like Antalya, then during the summer period, you need to do the opposite. You want to keep the indoor area cool by running certain machines such as air conditioning units. And the outdoor air will be hot. And without the insulation, the heat will be transferred towards the inside area. That's why we need one of the components as the heat insulation. Uh, if we want to provide a silent indoor area for the user, and if there is this source of noise in the outdoor environment, then the roof needs to keep the noise outside, or depending on the function of the building, maybe the inside. Uh, we need sound insulation. Um, If we want the building envelope to look nice, then we need finishes. And we can cover the outdoor surface of the roof with these finishes. The same can be applied to the indoor area. When the user looks at the inside surface of the roof, again, we need finishes if we want it to look nice. When the precipitation, because of the precipitation, there may be water problems in the building. Uh, and if we want to keep the water outside, then we need water insulation. These can be some of the components. We don't maybe specifically need different layers, separate products for providing these functions. However, this is mostly what we do. And uh, especially in order to keep the water outside, to provide water insulation. That's why we are doing it. We need to protect not just the user, not just the building, but the building products of the roof, all these other components of the roof, of the building structure itself, and all the other building elements. That's the first group that we need protection. And especially, we need to protect the space. When I say space, obviously, I mean the user uh, himself. Uh, what kind of problems does water cause, and how can we prevent them? Uh, we know that all the components that are created out of building pieces, and we use materials to shape these pieces. And the main building element is the structure of the building, which will include vertical columns, shear walls, or horizontal beams. We can prefer concrete, reinforced concrete, to create all these components. We know that concrete is a porous material. It has voids, lots of voids. And inside this concrete, uh, there are steel reinforcement bars embedded inside the concrete. When the water droplets are on the columns or shear walls on this concrete surface, due to these voids, the water will be emitted into the inside area. And when the water penetrates through the concrete and meets with the steel reinforcement bars, the water will cause the steel reinforcement bars to corrode. The corrosion, due to corrosion, there will be lots of problems, structural system problems, and during earthquakes or with the load transfer, there may be serious issues. not just the building structure itself, but all the other elements, such as this roof. We know that one of the components is the structure of the roof, and we can prefer timber material to create all the studs, rafters, and purlins. And if the timber pieces get wet, they they may start to decay. Again, this will cause a structural system problem for the roof. As they decay, they will lose their integrity, and the load transfer, the load carrying function may go wrong. Here we see a water damage, and that may be caused with the uh, liquid water or water in gas form. And uh, this is a different type of problem. Here we see mold. In Turkish, we call it küf. And the upper one, this image shows the humidity. It's the rutubet or nem in Turkish. Uh, we should be aware that these are not the equal things. Humidity is water in gas form, water in the air, in the gas form. And at a certain temperature, the air has a capacity to carry a certain amount of water vapor. If the limit is exceeded or the temperature drops down, the gas form, the gas, water in gas form will condense, which means it will liquefy. Uh, we see that especially in our bathrooms, the non-porous surfaces of glass, mirrors, or ceramic wall coverings, there will be actual water droplets. And that's a water problem. However, mold is a living creature. It's a type of mushroom. It doesn't look like that, but uh, it's in the same family. And we know that mushrooms are, they reproduce with these spores. They are like seeds for the mushroom. And when the when the conditions are available, such as there is enough food or light or humidity, especially, the spores starts to proliferate, and they create mycelium, which will create the mushroom itself. Mold is microscopic. It doesn't look like this mushrooms, these mushrooms that we know. We cannot see them with naked eye. However, especially in damp environments, these molds, they proliferate so much, they create so many mycelium that it starts to become, it becomes visible. And we can, because it's airborne, we can start to smell them because all these microscopic creatures, they can survive in the air for a significant period of time. And as we breathe, we inhale them. It can be very dangerous for us. Uh, that's the abstract building envelope. This part is the roof. These are the walls, and that can be the upper part of the foundation system, the grade level, let's say. And when there is water in the outdoor environment, depending on the properties of this building element, the product, it can it can be transferred towards the indoor environment. There are two main groups of building products. In the first group, we see porous substances such as concrete or these type of stones. It has voids, and they can be open pores, which will create tiny channels, and these channels will combine the outdoor environment and the indoor environment. It will let water droplets pass, water in liquid form or water in gas form to pass through. Uh, in the opposite group, we see non-porous substances such as glass or steel. They don't have any voids inside. That's why they won't let the water in. That's the main difference. And porous substances will emit the water, and they may cause the water to pass through. Non-porous substances, they won't let water in. And even if they have pores, the pores can be closed. Again, there won't be any voids for water to pass through. Let's take a look at this part, the upper surface of the foundations, the ground level, the grade level. Does the water stay on the surface for a significant period of time? We know that in the ground, there can be always water in liquid form or in gas form, especially when it rains, or there can be the underwater, underground water. We know that there's always water, and depending on the properties of the building products, if there are porous substances, the water can raise in the opposite direction of the gravity because of the capillarity, and there will be water problems in the indoor environment. Let's take a look at the vertical surface. What happens when it rains? We know that as the raindrops hit the surface of the walls, these vertical surfaces, they can cause the surface to get wet, but uh, because of the gravity, these water droplets, they won't stay there. They will just slide down, and as the rain stops, the wetness will dry off. Uh, but it won't be the same for horizontal surfaces. When it rains, due to the precipitation, the water may stay there for a long period of time, and that will increase the risk of water damage. That's why we need to come up with a proper solution. What can we do in order to prevent water problems? First, we can incline the surface. Instead of creating a totally horizontal surface, we can have a sloping surface, and that will help with the period of time the water droplets to stay on the roof. Again, with the help of the gravity, they start to slide down. Uh, we can keep the water away from the critical point. Here, in this example, all the water on this inclined surface will be collected, will travel down, slide down to this line here. That's the eave, and that will cause that will create the critical point. If we want to keep the water away from that line, instead of finishing that eave at the facade level, we can have a projected eave like this, and it will help the water to be away from that critical line. Also, we can either cover the surface of the porous substances with a non-porous material, or we can try to intervene and change the inner properties of porous substances, either try to fill all the pores or create a material with closed pores. But covering will be easier, obviously, and we can use either membranes, örtü in Turkish, or liquids or pastes. Membranes are the most effective ones, and we can create membranes out of bitumen. Bitumen is a side product of petroleum. When they are processing petroleum, they create bitumen, and that's the main ingredient for us to use to cover the roads for the automobiles. And in nature, we rarely find bitumen in its natural form. And as you can see, it's this half liquid, half paste, sticky substance, and it's very hard for us to create these membranes, stiff membranes out of this half liquid thing. That's why we need to modify the properties of the bitumen. We can either oxidize the bitumen, which means we need to blow hot air inside this bitumen, and the oxygen in the air will start a chemical reaction so that the physical properties of the bitumen will start to change. And with this change, with this chemical reaction, we will be able to create a hard enough sheet out of this liquid, or we can add thermoplastic resins to create a polymer bitumen. Thermoplastic resins, resin is reçine in Turkish. It's this sticky substance that we see on pine trees. It's the natural form, but this time we are not using this natural resin. We are creating a plastic resin, an artificial one, a thermoplastic uh, substance, and we add this substance inside the bitumen. And according to the type of the resin, the final product, the bitumen sheet, can be either plastomeric, which has atactic polypropylene. It's the name of the chemical substance, the chemical thermoplastic resin, in short form APP, APP. And the final product, the bitumen sheet, will become resistant against hot weather. If you are designing a building in a hot climatic zone, such as Antalya, Adana, or Africa, maybe, you can prefer this one, the bitumen sheets that has APP inside, and that's the plastomeric bitumen sheets. And the opposite, if you are designing a building in the cold weather, then you need to prefer styrene butadiene styrene SBS for short form. This sheet is only 4 mm thick. It's very thin. When we take a closer look, we see that it has different layers. All these layers, these 5 different layers, the combination of these layers will create this 4 mm thick sheet. Uh, Here we see, first of all, the modified bitumen. Depending on the climatic conditions and depending on our preference, it can be either SBS modified or APP modified. And the thickness of this second layer is approximately 1.5 mm. There is another one. We are getting two bitumen sheets and we are combining them with a non-woven polyester base. That's the base. It's like the sandwich. Inside the two bitumen layers, we have this non-woven polyester. Polyester, you can easily understand that that's a type of plastic substance. We know that poly means multiple, and ester is the single version. And non-woven means we are creating a sort of plastic fabric which is neither woven or knitted. In normal conditions, when we want to create a fabric out of the threads that we know, we need to either wave the threads, uh, that's the example of a wave, or we need to knit, uh, creating little knots uh, using that thread. And non-woven fabrics, we are creating these plastic fibers, thin fibers like threads, and we are combining these, bonding these fibers, not by weaving, not by knitting, but using some sort of chemical or mechanical method. We are combining them using either heat or solvents, something like that. And that base, that non-woven polyester base, will work just like the reinforcement bars in the concrete. You know that concrete is resistant against compression strength, compression stress, but it's weak on the tension. Uh, that's why we need steel reinforcement bars where the tension occurs so that the reinforced concrete will be strong both on the compression and the tension. The base will work just like the steel reinforcement bars. It will help to increase the resistance of the bitumen sheet against tearing. It will strengthen the bitumen sheets. And the top surface and the lower surface will be covered with polyethylene. Again, a different type of plastic substance, poly, multiple, ethylene. Ethylene is the single version, single molecule, and we create this chain of molecules by polymerization. And that's the thin, transparent plastic sheet. It's very thin, and the total thickness becomes 4 millimeter. Of course, in order to cover this bitumen sheet, we need a smooth surface. And you know that if we are designing this type of load transferring roof, or maybe the suspended roof, we have rafters, a series of rafters, and uh, they have gaps. If we want to place thin bitumen sheets over the rafters, the bitumen will sag. It won't be able to hold its posture. That's why first we need to cover the upper surface of these rafters with artificial timber planes, engineered wood panels. I think you remember we covered this last semester. There are 5 different types that we can prefer. This is plywood. In Turkish, we call it katmanlı ahşap levha or counterplak. Uh, Counterplak is the common name, you know. Here we have natural, very thin wood panels, and we place them on top of each other. We glue them, and we create this plywood. It's very good in terms of load-bearing capacity. The load-bearing capacity of this engineered wood is very high. H is for high. And the durability against water and negative conditions is also very high. It's very durable. It's very resistant against all these negative conditions. So we can prefer plywood to cover the upper surface of these rafters. Or there is this second alternative, which is called chipboard or particle board with synthetic resin binder, resin reçine. Synthetic is the artificial, not natural, but synthesized resin. And we have lots of chips, tiny chips of wood, and we can get this resin binder and we can glue all these different types of chips together into this board. In Turkish, we call it sentetik reçine bağlayıcılı ahşap yonga levha or sunta. Sunta is the common name. This synthetic resin binder is water soluble. When this chipboard gets wet, the binder dissolves and uh, we have dust-like chips. So this is not very good. In terms of load-bearing capacity, its load-bearing capacity is low, L for low, and so the durability against water and negative conditions, it's low. We shouldn't prefer these type of engineered wood panels where there is this high risk of water damage, such as roofs. In the third group, we have oriented strand board, yönlendirilmiş talaş levha, OSB. OSB is the short form of oriented strand board, OSB. Load-bearing capacity is very high. Durability against water and negative conditions is average, not very high, not very low. It's in the middle. So this is another alternative that we can prefer for roofs. We have chipboard. I forgot the D here. It needs to be board, chipboard. Again, we are using the same type of particles, but this time the binder is not synthetic resin, but it's cement. Çimento bağlayıcılı ahşap talaş levha. The brand name is Heraklit. Heraklit, not the name of the product, but the brand that produced this product first in Turkey. That's why it's known as Heraklit. Load-bearing capacity is very high because it has cement in it, and so the durability against water and negative conditions, it's very high due to cement. It's not affected negatively from water. That's another alternative that we can prefer for roof. And in the last group, we have fiberboard, leaf levha. It can have two different densities, MDF, HDF, middle density fiberboard, high density fiberboard. MDF is the common name, and it's short for middle density fiberboard. Load bearing capacity is high. Durability against water and negative conditions is high. Uh, we can prefer all four of these engineered woods except chipboard, sunta, because of the resin binder. And once we cover the upper surface of the rafters with these engineered woods, we can apply the bitumen sheets using blowtorch. Blowtorch, şalumo in Turkish. When we apply the blowtorch, the outer layer of polyethylene film will melt down, and it will cause the bitumen to melt down. That's how we can fix, adhere the bitumen sheet over the engineered wood panels. And we need to start at the eave level. First, we place this long sheet, and then when this line is covered, we need to go to do the upper line, and they need to overlap for 10 centimeters. The upper line needs to overlap the lower one for 10 centimeters. We do the second line, and then we proceed our way for the third line, and it goes like that till we reach the ridge level. Instead of creating load transferring roofs using these timber or steel pieces like rafters and purlins and studs, we can have these inclined reinforced concrete floor slabs, or we can have these AAC panels. Once we do that, we already have a smooth surface, and we can apply the bitumen sheet over these inclined surfaces. We don't need to use these engineered wood panels anymore. And again, we need to do the same. We start with at the eave level, apply the first line, and then go to the second line. They need to overlap for a certain amount of part, like 10 centimeters or something. But when we are doing this application over the reinforced concrete surface, we know that concrete is a mixture of these different materials, such as water, cement, and aggregates, fine aggregates like sand, and coarse aggregates like crushed stones. All these crushed stones, they have sharp surfaces. And because of these aggregates, the finished surface of concrete can have these sharp angles or sharp points, rough surface. If we apply this very thin 4 millimeter bitumen over these sharp edges, then there is this risk of tearing. The bitumen sheet can be teared, and once it's teared, there's no protection from water. This will create a risk for water damage. That's why we need to first look at the surface of the concrete, and if it's rough, if it has this rough edges, then we need to cover this surface, the upper surface of concrete, with leveling concrete. They're the same. The lower is the concrete, the upper one is also concrete. But what's the difference? Leveling concrete is the mixture of water, cement, and aggregate, but for the aggregate, we only prefer fine sand. We don't use crushed stones. We use only fine sand. That's why we have a smooth surface. And the thickness of this leveling concrete can be approximately 2 centimeters, 2.5 centimeters, or 3 centimeters, depending on the roughness of the lower surface of concrete. And now we have a smooth area that we can apply the bitumen sheets without the risk of tearing. But first, we need to apply primer coating. Primer coating is the liquid bitumen. First, using a roller brush or a regular brush, we cover the upper surface of leveling concrete with liquid bitumen, and then we apply the bitumen sheets in 2 layers. As you can see here, this is the first 4 millimeter layer, and above that we need to apply a second 4 millimeter layer. There needs to be 2 layers of bitumen sheets, and once we apply the blowtorch, the polyethylene film of this bitumen sheet will melt down, and this primer coating, the uh, mm, liquid covering of the bitumen and the bitumen of the sheet will melt down so that they will be adhered to each other. That's why we first use primer coating. And once we do the water insulation, we can proceed our way for either heat insulation or the finishes over this water insulation. The direction of the slope is important when we are doing this application, and we need to start, that's the direction of the slope, that's the lower side, the eaves part. We need to start with the eave part, and first we have this long bitumen membrane sheet. That's the first line. I place the first sheet, and once it's finished, I don't do two sheets to be combined end to end like that, because when I do that, I create a higher risk of water leakage. Instead of combining them end to end like this, I need to overlap the second piece over the first one like this. They need to overlap for 10 centimeters. And the first line will be finished. Then I need to go upwards for the second line. Again, I need to overlap this third piece over the first one, and fourth piece over the third and the second one, as you can see, for again 10 centimeters. And I need to go upwards till I reach the ridge line like that. And that's the first layer, the lower layer, directly above the leveling concrete. And over this first layer, I need to do a second layer. I need to do the whole process one more time. But this time, this piece needs to be centered based on the joints of the first layer. As you can see, I'm placing this upper layer, the first piece of the upper layer, centered based on the lower layers joint. I need to do the overlapping one more time and do the second layer and the third layer and go up like that. This bitumen sheet is water resistant, which means it won't let water in liquid form to pass. And it's also vapor resistant, which means this very same bitumen sheet won't let vapor, water in gas form, to pass. If the lower space, indoor space, is a kitchen or a bathroom or any other space that produces lots of water vapor like this, then all these excessive vapor, the water in gas form, will raise above, and all the other layers like this reinforced concrete surface or this leveling concrete, because they are porous, they will let the water molecules, gas molecules, to pass through the section. However, because the bitumen sheet is water and vapor resistant, the water molecules in gas form will not be able to pass through, and they, based on the production level of the gas, the membrane will start to balloon up, and that's dangerous because with the pressure, lower pressure of the gas, there's this risk of tearing again. That's why we need to prevent it. And instead of placing the water insulation membranes directly on the surface of the either the roof sheeting or concrete, leveling concrete like this, we can slightly elevate these membranes over the surface of the porous substances and create a channel, an inclined channel, so that the gas, water uh, in gas form can be collected in this channel. And if we let a natural air circulation through this channel, we can sweep up the excessive gas. uh, how can we do that? We can have this air intake at the eave level. We can create tiny gaps uh, here at the eave level and let the natural air to pass inside this channel. And through this channel, we can circulate the air and sweep away the excessive gas. And at the rich level, again, we can create tiny little gaps which won't let water to come inside, but the air to pass through easily using these type of plastic uh, substances. It has these tiny air gaps uh, positioned in this line here. And this natural ventilation, this airflow channel will help with the snow problem in cold climates. We know that there is the snow accumulation on the roof, and at the eve level, the snow, the melted and frozen snow can cause these icicles. This can be very dangerous, and it can cause some water damage as well, because this projected eave here, the lower part and the upper part, it's cold. It's in the outside environment. The lower part, there's this cold air, and in the upper part, there's this also cold air. However, it's not same with this other part of the roof, because this has the indoor area. This is the indoor area, and mm, because of the heating system, we have this hot air, and we know that air raises towards the upper direction, uh, like this, including all the excessive water vapor. And this hot air and water vapor can pass through the uh, porous substances. It can cause the snow to melt at this level. Once it's accumulated towards the eave, it will refreeze again. And this can cause water leakage due to accumulation of snow at this eave part. The icicles can be formed, and it can be dangerous. If we cannot do this tiny channel like that, we can have a ventilated roof space like this. This will help to sweep away the excessive uh, thing as well. As the second alternative, instead of using membranes made out of bitumen, we can change the material of this water insulation, and we can have membranes made out of plastic, not out of bitumen, but out of plastic. And we can use only one layer, not two layers on top of each other, only one layer. Tyvek is the known brand name, very famous brand name. It's a specially produced type of plastic, and it has micro pores. These pores are specially engineered. They won't let water in liquid form to pass, so that it's water resistant. However, these tiny microscopic voids can let the vapor to pass. Vapor, water in gas form, it's not vapor resistant, it's vapor permeable. It will let water in gas form to pass, but it will hold the water in liquid form, and it won't let it pass. Then we don't need that air circulation channel. We can just directly apply this plastic membrane over the surface, because all this time all the layers in the section will let the vapor pass like that. Okay, we covered the water insulation. A new question now. How can we prevent unwanted heat loss or unwanted heat gain? We need heat insulation. Also, not today, but in near future, hopefully, we are going to do the sound insulation and some of the same principles that we can use for the heat insulation will help with the sound insulation. If the outdoor air is cold and if we are trying to heat up the indoor environment, and if we don't mm, provide sufficient heat insulation, not just for the roof, but for the whole envelope, then the heat will travel through the section and there will be heat losses. And that's something that we need to prevent. The opposite version can be during the summer period where we want a cooler air in the indoor environment, but the outdoor air will be so hot, so that the heat will travel through this section starting from the outdoor environment towards the indoor environment. Again, we need heat insulation. This time, for a sufficient heat insulation, we need gaps. We need porous substances. We know that non-porous substances such as glass or steel, they transfer the heat very quickly. These are the compact products. Just in this example, we can see the same thing. There's this metal spoon, and there's this plastic spoon and the wooden timber spoon. There's this boiling water. The tips of these spoons are dipped into the hot water, and they placed a piece of butter in the spoons here. The butter in the metal spoon has already been melted because the metal, it doesn't have any pores. It's a non-porous, a very compact substance. It transfers the heat so quickly. That's why the butter is already melted. In the opposite part, we have timber, which has lots of voids, channels. That helps with the decreasing the heat transfer speed. Uh, we cannot stop the heat transfer altogether. We can slow it down because the gaps will help to decrease the speed. The heat is mainly transferred from molecule to molecule. As there is less gap, that means there will be more molecules next to each other, neighbor molecules, which will speed up the heat transfer. That's why we prefer these type of wool jumpers or sweaters during the cold weather, because let's imagine that's the upper surface of our skin, and due to our metabolism, our body produces heat all the time. Without this protective layer of wool, the heat will be transferred so quickly. That's why we start to feel cold. However, if we cover ourselves with this type of thick wool sweaters or blankets, then all the trapped air inside these fibers uh, will help to slow down the heat transfer process. Just like these wool jumpers or blankets, we have glass wool or rock wool cam yünü, taş yünü in Turkish. They are like thick blankets, very thick blankets made out of actual glass or some sort of volcanic rocks. First, they get these solid pieces, and in a factory, they create these very tiny fibers, very thin, very lightweight fibers, and they collect lots of these fibers and create this glass wool or rock wool thick, like 5 centimeters thick insulation boards. They have lots of trapped air inside, and as you apply pressure, you can squeeze them easily, and they are very lightweight, of course. In the second group, we can have EPS. PS is polystyrene. Poly is for multiple, strand is the name of the molecule or monomer. It's the single chemical substance, strand monomer. And if we polymerize, which means multiply this strand monomer into a chain of monomers, now we can call it a polymer. Uh, it's not a single monomer, it's the chain of multiple monomers. That's why we can call it polymer. We have the strand polymer, polystrand, and E is for expanded. First, we create one of these particles, and we then apply heat, a certain amount of heat, which expands the particle, and we collect all these tiny expanded particles and create these boards. When we take a closer look, that's what we are going to see. The same XPS, the only difference, polystrand, polystrand, the same polymerization. These particles are not expanded but extruded. Extrusion is the name of the method or how these boards are created. There is this pool of polymer, polystrand, and they force this melted half liquid plastic substance to pass through this tiny gap. And in the opposite side, we have these uh, boards. We don't see the tiny bubbles anymore. It's a more compact substance. Glasswool, rockwool, EPS, XPS. Let's take a look at their heat insulation level. We want a high level of heat insulation, and we see that this group has a very good level of heat insulation, very high level of heat insulation. Also, this group. The fire resistance is important now. These are non-combustible. You won't be able to burn these substances because of their material, the glass and the rock. You cannot be able to burn rock. However, because these are plastic, these are highly inflammable. A very high risk of fire in terms of EPS and XPS. Water resistance, these are very bad in terms of water resistance because of all the tiny air gaps inside the fibers. Once they are wet, they emit all the water, they become very heavy, they lose all their heat insulation abilities, they become useless. But because these are plastic in the second group, they have a very high level of water resistance. Uh, this first group is bad in terms of pressure resistance. You can easily squeeze them when you apply pressure. These are relatively, in the second group is relatively better in terms of pressure. The price, this is average, that's very low. We have a third group. We see that its heat insulation, fire resistance, water resistance, and pressure resistance is very good, but the price is very high also. You remember that last semester when we are doing the foundations, we provided heat insulation for the foundations. We covered all the foundation columns and these grade beams with XPS because we will be burying all these plastic substances, plastic heat insulation membrane boards inside the damp earth. The fire risk is pretty low there. And because there will be so much water inside the ground, we want something, a cheap substance, which has a high resistance of water. That's why we preferred XPS or EPS there. However, for the facade, for the roof, fire is a high risk now. And that's why we need to avoid plastic substances, highly flammable substances, to prevent the heat fire problem. Okay, where are we going to do the heat insulation? We can either prefer glasswool and rockwool for roof. We need to avoid plastic substances because of the fire risk, or we can prefer glass foam. Preferring glass wool and rock wool will be better in terms of sound insulation. So let's keep that in mind. But where are we going to place these heat insulation boards? We have different options here. If the space in between the rafters and the floor area, the ceiling of the top floor, if this space inside these two surfaces is not going to be used by people, then we can prefer glasswool or rockwool. But if they are going to be used as a space, if people will walk on these heat insulation boards, or they are going to place heavy furniture over these boards, then it will be compressed and it's not good. Then we can either prefer glasswool or rockwool, which is enhanced in terms of pressure resistant, like this, something like this. Or instead of placing these boards over the floor surface, we can place them between the rafters, like this. We can have glasswool or rockwool, and we can cut them into this width of the gap between the rafters, and we can cover this gap with these glasswool and rockwool surfaces. But this will be also good in terms of suspended roofs, because we know that there is no available floor surface, so we won't be able to place these boards over the floor surface because there's no floor there. Then we can prefer using these heat insulation boards between the rafters. The third option can be using plastic substances, but maybe these XPS or EPS boards can be enhanced in terms of fire resistance. And you remember that we covered engineered wood panels over the rafters for a smooth surface. Instead of these engineered panels, we can use heat insulation panels. These are thick, their pressure resistance is high, and if they are enhanced in terms of fire resistance, then we can cover the upper surface of rafters with these heat insulation boards, which can be made out of EPS or XPS. These are also water resistant, so there won't be a problem with the water. And we can apply the roof finish directly over these heat insulation boards. So we have three alternatives. If the space in between the rafters and the floor is not going to be used, then we can cover the upper surface of this floor area. But if it's going to be used, instead of because of the pressure, it will be crushed. We can use the same materials between the rafters like that. That's the second alternative, and it will help with the suspended roofs. Or as the third alternative, instead of these engineered wood panels used as the roof sheeting, we can use heat insulation panels. These have a high pressure resistance, a high water resistance, and we can apply the roofing directly over these heat insulation panels, and that's the third option. How can we finish the roof? The finish component, the upper part of the roof, uh, there can be many different alternatives. We are going to use pieces, but the most common ones is the pieces that are made out of clay, metal, such as lead, copper, zinc, titanium, or bitumen again. And using these clay material, we create clay roof tiles. We can apply them over the insulation layers. Using these metal material, we can have sheets made out of lead, made out of copper, made out of zinc or titanium. We can apply them. And this bitumen can be used to create tiles, asphalt shingle tiles. Uh, and we can use these tiles to cover the surface of the roof. Uh, these clay tiles may be in different forms. This is one of the most common ones. We are very familiar with this form here. And these are called clay interlocking roof tiles. In Turkish, we call them Marsilya tipi kiremit. The sizes can be this length is 410 millimeters. This width is approximately 210 millimeters. These sizes can be different from company to company. Different companies may produce different types of tiles. And we start to lay these tiles just like the water insulation, we can start at the eave level. First, we lay the first line, and the second line, these pieces will be over the first line. They will overlap for a certain amount of length. And as you can see here, these joints in between each of these tiles, they are different. They don't create a same line, a straight line. In order to do that, the second line will start with the half of these tiles, so that the joints will be staggered. Joint in Turkish is ders. Joint is the term that we use to determine the line when two different pieces meet. These pieces can be there's this joint, and these are a straight line like that. In Turkish we call it dersler şaşırtılmalı. Dersler şaşırtılarak oluşturulmalı diyoruz. Okay, here you can see this is the section of one of these tiles. There are grooves or tongues, we can say. And this upper part here, it looks like a channel, which we can call a groove. And when we are laying these tiles, starting from the ear point and going upwards, the second line, the tongues of the second line will be inside the grooves of the lower line here. And it goes like that till we reach the ridge level. This helps with the water transfer. We don't want the water droplets to pass through these tiles towards the inside layers of the roof, the lower components. When it rains, these tiles are inclined over the inclined surface of the roof. The raindrops will start to glide down with the help of the gravity, and it will just slide down. And it doesn't create a problem, even if all these water droplets enters to these channels here, because as you can see, next to this horizontal channel, there is this vertical channel. It's combined, so it continues like that. And this other section, this is the long section like that. And if we cut it like this horizontally, then we can see the channel, this side channel, in a better way. And the other part, it creates a single tongue like that. And when we lay them next to each other, again, the tongue and groove connection, we have the tongue and groove connection. And as the water droplets enters to the groove here, it will glide down. It will help the water to glide down to next to this channel here, and it will pass down. Okay, we are laying these tiles next to each other. We create the first line, but how can we prevent them to slide down themselves and to be broken like that? We can use lats, timber lats, çıta, ahşap çıta. And first we can nail these lats over the water insulation or heat insulation, depending on our choices. And then we can use these tiny parts here, tiny tongues here, to be placed over these lats. And it will prevent the tiles to slide down like that. Okay. Also, if we want, we can use these type of tiny metal sheets, hooks, let's say, and we can nail them over the lats, and the side of the hook will hold the tile. There can be specially produced tiles for these hips, like that, and the ridge like this, and the ends of these hips can be covered with these end tiles. There's this brand which produces specially mm, shaped, waterproofing, very hard panels made out of bitumen, and these are large panels, as you can see. The brand name is Ondulin Avrasya, and its product is called Isoline. Uh, you can place these directly over the rafters. You don't need engineered panels sheeting, and they have these grooves uh, which you can place your tiles directly without the need for timber lats. And the channels, as you can see here, these have uh, embedded channels, vertical sloping channels, which will help with the natural air ventilation, and it will sweep all the excessive water vapor, and it will prevent the formation of icicles. In the other group, we have again clay tiles, but in a different form. These are called mission or Spanish tiles. In Turkish, we call them Alaturka pyramid. And we have it's like the half cone. It looks like the half cone or half cylinder. But these arcs, they have slightly different diameters or radiuses, let's say, and we get lots of these tiles. First, we place them over the lats, looking upwards like this, open. We place them open. Again, we start at the eave level, first line, and then once the first line is finished, we do the second line. And as you can see, the narrower end of the upper line will be placed inside the wider end of the lower line, and they're again overlapping, and they are slightly separated from each other. There's this slight gap in between these rows, let's say. And once you have the ridge line, then you start to use these opposite sided ones to cover the gaps like that. As you can see, once you cover them all, again, you do the same thing. You are doing the same method. You start at this eave level and proceed your way up to the ridge level. Now, once you do that, the lower level will create sloping channels, and the upper level, upper layer, will create these inclined surface. As the water droplets hit this uh, inclined surface, the water will either follow the path towards the left channel or the right channel. It doesn't matter. Once it's inside the channel, there is no other choice than the water to glide down to the eave, and the sizes can be different based on the company. Like this A can be 420 millimeters, this B can be 160 millimeters. Isoline, sorry, Ondulin Avrasya has created mm, these hard panels made out of bitumen for mission tiles. These are called Rufoline this time, and you can use metal strips to fix the tiles over the surface of this hard panel. And again, the channels, these continuous channels, will help with the natural ventilation. And as you can see, you can fix the tiles using these metal hooks, special metal hooks. You can nail the hooks on the insulation, water insulation, and you can use smaller ones to combine two of these tiles to each other. Clay tiles are covered. Let's move on to metal sheets. We can prefer lead, copper, zinc, or titanium. And once we do the heat insulation and water insulation, the roof surface is ready for finishes now. And these sheets of metal are very thin, and we can have them sized in this bigger panels, and we need to cover the whole surface of the roof using these very thin metal panels, but we cannot nail them, we cannot bolt them, we cannot glue them on the surface of the roof because of expansion. As the heat of sun rays hit the surface of these metal sheets, the metal wants to expand, which means it will change its dimensions. It wants to become bigger, genleşmek in Turkish. And if we fix these sheets, the expansion cannot happen. And because of this change in the dimensions, it will cause the sheets to be broken into pieces, to be tiered. And that's something that we need to avoid. We cannot just lay them as they are. With the wind, because they are very thin, the wind will fly them off. We need to come up with a proper way to fix them, which will prevent the flying and which will allow these sheets to be expanded. As you can see, we need to cover the whole surface. That means we need lots of pieces like this. We are going to place them next to each other and on top of each other like this till we cover the whole surface. Let's take a look at this combination. We can use a specially produced interlocking method to combine two sheets together. This horizontal joint can be created like this. First, we need to fold the sides of each panel like this. This one will be folded like that. The upper one will be folded like this, creating some sort of hook like that. And we combine them. The upper one is at the upper level, as you can see, and as the water droplets hit the surface, with the help of the gravity, because they are inclined, here you can see the section like this, the water will glide down. There is no risk of water to be penetrating inside the components of the roof, inside the lower level layers. That's for the horizontal combination. What about this vertical line, vertical joint here? In order to fix these two panels together, again, we need to fold the sides of these panels. Also, we are going to use an L-shaped third piece. First, we get the piece and we can nail this piece only at one point on the surface of the insulation. Here, as you can see, this L-shaped piece is nailed using only one nail or bolted maybe. So this is fixed, and the side of this left panel is folded. The side of this right panel is also folded. We have three layers next to each other, three metal layers next to each other, and we start to fold them one time and two times, twice. We do this twice, fold, and here, as you can see, this section will look like that. And as the rainwater hits the surface of the metal, it will again slide down, and there is no way the water to climb up inside this fold. This is called interlocking method. With this method, all the sheets will be free to expand, but they will be locked, fixed on the surface of the roof. That's why we use these strips when we look at the old structures like the domes of the mosques, many of the mosques. These are covered with sheets of lead. This is lead. As you can see, their sides are folded, and when there are two strips next to each other, we see this line. And if you take a closer look, you can see the horizontal combination here as well. We know that steel is oxidized, and once it's oxidized, the rust is formed, and it will end up in corrosion. Stainless steel, there's no risk of corrosion because it has chromium inside, and as the chromium molecules react with the oxygen, a passive chromium oxide layer is formed, and this is a protective layer. It prevents the molecules of iron to be connected with the molecules of oxygen. So there is no risk. Even if we cut it, we disturb the passive protective layer. Instantly, the oxygen and chromium will react and recreate the layer. That's why we don't get any rust or corrosion in stainless steel. It's same with the aluminum. In aluminum, we don't see corrosion or rust because the oxygen molecules in the air will react instantly with the molecules of the aluminum. So the passive aluminum oxide layer will be created as a protective film. Here we see lead. It's a very soft metal. You can easily bend it without using very much power. That's kurşun. Copper, bakır. We see rust in these metals, in lead and copper. However, we don't see corrosion. Corrosion is the end result of the rust in steel. We see rust in these metals, but we don't see corrosion. There is no risk of corrosion because just like in the stainless steel or aluminum, as the molecules of copper and lead will meet with the oxygen in the air, a special type of rust is produced, which we call patina. It has this turquoise color. The original color of Statue of Liberty is this reddish brownish color, but in time, due to this patina, this special rust, it turned into this turquoise color. In the third group, we see asphalt shingle tiles made out of bitumen, just like they create the water insulation sheets. They can use the same technique to create specially produced tiles. You remember that we have polyethylene film as the topmost layer. This is a very thin and transparent surface. And as the sun rays hit the surface with the increasing heat, this will start to melt and it won't be protective for the bitumen membrane. They are using the same type of lower layers. They only change the upper one. They are not covering the whole surface with polyethylene film. Instead, we can prefer fine sand. As you can see, the lower layers, they are the same. We have the modified bitumen layer, non-woven plaster as the base, and a second layer of modified bitumen, either SBS modified or APP modified. The lowest layer one can be polyethylene film as well. The only difference is the topmost layer is either can be fine sand, the whole surface can be covered with fine sand, just like this one, so that the bitumen membrane will be protected from the heat of the sun. Or we can use these bricks or ceramic tiles, and we can uh, convert them into fine sand like this, powder, and we can use this grains to cover the upper surface of the bitumen. The lower ones will be the same again, the modified bitumen, the base, and the polyethylene film as the lowest one. And this is called asphalt shingle, and they create these strips. They have two parts. This is the sticky one. It has this its own adhesive surface, and that one is the seam one, the seam surface. And we can use these strips to cover the whole surface of the roof. It can be adhered using this part, and the higher line will overlap. So that the end result will look like just like the clay tiles, very similar to the clay tiles, or we can staple them directly over the surface of the roof sheeting, and that's it. That's the roofing. Now let's take a look at the drainage system. How can we remove the water off of the roof surface? Uh, you remember that once it rains, the whole water will be at this uh, eave level, and that's a critical point. And we don't want the water to flow freely. It will cause aesthetical problems on the facade with all the dirt and dust on the surface of the roof. The facade will be stained, and that's something that we don't want. Also, we don't want the users to get wet while they are trying to enter the building through the door. Instead, we can collect the whole water, rainwater, in a channel like this, and then we can drain it out. That's what we call a drainage system. It will be uh, made out of two main parts. The first one is the collection of the water. Here, this channel is called a gutter, oluk in Turkish. And once we collect the water in this channel, this half channel, the gutter, we can transfer it using these pipes. That's called downspout. Uh, Yağmur iniş borusu in Turkish. Uh, we can hang the gutter uh, to the side of the eave, and we need to connect the downspouts depending on this distance. Maybe if it's a short eave, then we can have only one downspout, but if it's a long eave, then we may need more than one pipe system, let's say. And uh, their connection, there's this empty hole in the gutter. That's where we connect the downspout, so the water will be directed towards this connection point. That's why we need to provide a certain amount of slope for the gutter. Maybe 1% or 0.5% will be enough, so that the water will be directed towards the downspout, and it will be transferred safely. We can hang the gutter using these hooks. These are called hooks, kepçe in Turkish. We can nail them on the surface of the roof sheeting or on the surface of the rafters. Here, this is a nice example. These are the rafters, and we see that the sheeting is slightly elevated from the surface of these rafters using these lats, so that there is this sloping channel, continuous channel, and the entrance of this channel is protected with this thin wire, so that there won't be a bug problem or bird problem or something like that. But it will let the air pass at the eave level behind this gutter, and the air can be circulated towards the ridge point. It can sweep all the excessive water vapor like this. Here is the section you can see the air circulation, and that's the gutter, the section of the gutter here, and this is the elevation of the side view of the hoop. Uh, we don't want our gutter to be clogged with all these vegetative pests like that, so we can provide some sort of protection for the gutter. And we can use these straps. These are called straps, kelepçe, kelepçe, to hang the downspouts like that. Downspouts are pipes. They can be made out of metal or PVC, uh, something like that. And if we want to connect two pipes end to end like that, we can prefer a socket like that. The lower pipe can have a slightly larger part at the end. This is called socket or muf in Turkish. That's the name for Turkish term. And just under the socket, we can place the strap. With the help of the gravity, the pipe will be sitting on the strap, and the strap will be connected to the facade of the building, as you can see here. And the above pipe can be placed inside the socket here, as you can see, and it will hold tight inside the socket like that, and the water coming from the gutter will be transferred directly downwards. There's no way the water will climb up like this, so there won't be any water leakage problem. This socket will help with the straps, with the fixing of the pipes onto to the facade, and it will help with the water leakage. There will be no problem with the water leakage. We can let the rainwater to flow freely at the end of the downspout. However, this will cause some stains or water problems here at the grade level. Instead, we can connect the downspouts to stormwater collection channel, and we should never connect the downspouts to sewer, because if it rains so much, if there is this excessive water, then it will cause the sewer system to create a problem. You will have this return at your toilets. That can be very dangerous. Or, as a third option, you can collect all the rainwater in an underground tank, and you can purify the water and recycle it to be used one more time in your building. If you don't want to see the gutter and the downspout, you can hide them behind the wall covering and roof covering like that, and you will see only one line here. However, behind this finishes, there is this gutter and the downspout. But this covering surface needs to be easily removable, so that if there is a problem with the gutter or the downspout, you can be able to remove the water covering, wall covering or roof covering, and change the piece or fix the problem, and then close and hide it one more time. Okay, drainage system is being covered. Let's move on to our last subject now. This is the question: how can we design flat roofs? In flat roofs, instead of the sloping surface, we have an almost horizontal surface. And it has the same three layers. First, we have the roof structure, then we can place our insulations, and the last layer can be the finishes. Roof structure is the normal floor that we learned how to design last semester. We can either prefer reinforced concrete floors, flat slabs without beams, flat slabs with beams, or depending on the span, we can either prefer ribbed slabs or waffle slabs. These are the alternatives that we can prefer for reinforced concrete, or instead we can prefer metal decking with these metal structure, steel structure. We can have these trapezoidal steel sheets and place concrete over that. Or if we are designing a timber structure, then we can have timber decking, which we can uh, cover the upper surface of these girders and beams with engineered panels. And over this structure, we can place the same type of insulations, either bitumen membranes or plastic membranes, or or let's say glasswool, rockwool, EPS, XPS, or glass foam as the heat insulation. And over these insulation, we can place the finishes. But I said almost horizontal. Uh, it looks like it's flat. However, we call it flat roofs. However, we need to provide a slightly sloping surface. Otherwise, the water will stay there, and we don't want that. We need to collect this water and direct it towards the drainage system, and we need to get rid of that water, even if it's the flat roof. Uh, for this, we are using drains just like we use on our bathroom floor. That can be a singular drain like that, which we can collect all the water, and then we can connect it to the downspout and get away the water. In order to do that, you remember for flat roofs, we need these parapet walls mostly. We can have a hole inside the parapet wall, so that we can place our drain here very close to this hole. It will be embedded inside the layers. Only this upper part will be visible, so that the water can be collected, and this lower part, embedded part, will be connected to the downspout here. We still need slope. As you can see, they have, in this example, we have sloping surfaces. If the rain comes here, then it will be directed towards the drain. If it comes here, it will be directed towards the drain as well. Here also. But the slope will be only 2%. The minimum will be 2%. Maybe if you want, you can do 3%, 4%, and that will be enough. Once it's in the drain, you can use this hole to place a pipe which will direct the water towards the outdoor area, and then you can collect the water in a box like that, and the box will be connected to the downspout, and you can get the water away from your roof surface. Uh, that's the flat roof. Either you can create a single slope, 2% slope, and direct the water towards this channel. Instead of a singular drain, you can use a channel. Again, we call it the valley and ridge, like that. And this water, the whole water, will be collected in this channel, and then at a single point, you can direct it towards the outside and connect it with the uh, downspout. This is an example. The 2% slope can be created like this. This is the lowest part, and this is the highest part. And throughout this distance, it will start to be thicker and thicker, and the section will be like that. And this thickness here, let's call it X centimeters. It's related with this length of the roof, this length of the roof, and the percentage of the slope. If I increase the percentage, it will get thicker. If I increase the length, it will get thicker as well. It's related with the length and the percentage, the slope of the roof. Uh, I can create this inclined surface, 2% sloping surface, using leveling concrete. The same leveling concrete, the only difference, you remember that the leveling concrete is the mixture of sand, fine aggregate, water, and cement. Uh, the only difference is the previous leveling concrete, it has this horizontal surface. Now I'm creating a slightly sloping surface, and I don't want my leveling concrete to get very thick like that, because all this leveling concrete, the sloping surface, will be resting over the floor slab. And I don't want a very thick layer of sloping surface because as it gets thicker, it will become heavier. I don't want a heavy layer over my floor slab. Uh, for that, to decrease the weight of this layer, I need a thinner slab. I don't want a very thick leveling concrete. Either I can decrease the slope of the uh, surface, or I can try to decrease this length of the roof. Or as a third option, instead of using leveling concrete, a very heavy material, I can change the material. Instead of concrete, I can use heat insulation panels, which are produced with these increasing thicknesses. As you can see, as we place the heat insulation, we will be providing a sufficient heat insulation, and also we will be creating a sloped surface for our flat roof so that we can direct the water towards the drainage system. This will be a better option. In this example, you are seeing a specially produced rockwool, which is enhanced against water damage. It doesn't get wet, and it's not affected negatively if it's wet. Instead of creating a long channel, we can collect all the water at a single point using a point drainage like that. For this, we need to create two sloping surfaces, and their combination will create a valley. This will be the ridge line. The first sloping surface will be in this direction. The second one will be in this direction, and their combination will create a joint like this, which we call a valley. And the top view will look like that. This is the triangular surface with this direction of slope for 2%. And this will be the other sloping surface. It can have the same slope, 2%. And this time the direction will be towards the drainage system like this. And as you can see, we prefer it with square or close to square roof surfaces. The sides, this one and this one and this one and this one is either equal or almost equal. With this square shape, you can use the same amount of slope, 2% for two panels. Uh, Here is the example. Let's imagine that we are using a reinforced concrete slab with beams. The thickness of this floor slab is 10 centimeter, and that's the top view, and this is the section. 10 centimeter floor slab with the beams at the sides like this. And over this floor slab, first we place the water insulation, or not the water insulation, sorry, directly the drain, the singular drain, which has this side pipe. The drain will collect all the water and it will direct the water towards the side pipe, and the side pipe will transfer the water towards the outside area, and then down with the downspout, the water will be collected and transferred away. Here, In order to create these sloping surfaces towards this drainage system, I need to first create this sloping surface, either out of leveling concrete or using a heat insulation layer like that. As you can see, that's the lowest thickness, the thinnest part of the sloping surface, and it will meet with the drainage system. And it starts to increase slightly with the slope, and that's the thickest layer. I need to do the calculation and I need to change the material if it gets too thick. That means it becomes too heavy. That's the first side of the sloping surface, and the top view will look like that. And I need to create one more time. As you can see, the same thickness here, all the side, and then it starts to descend down towards the drainage system. And that's how the drain is placed, like that. And this is the top view, like this. Of course, I don't want the water to be poured at the sides of the roof. That's why I need parapet walls. I need to stop the water. I don't want it to be look bad at the sides. Here we have the parapet walls. These are tiny walls that has like 40 centimeters or 30 centimeters high. And for the floor, we used reinforced concrete. If we prefer a different material for the parapet walls, not a reinforced concrete, but maybe brick walls, then the whole brick wall will be fixed, connected to the upper surface of this reinforced concrete with a mortar. A cement mortar that will has this thickness of 2 centimeters or 1.5 centimeter, a very thin surface, very thin layer of cement or mortar. The whole brick wall will be fixed over the reinforced concrete with this thin mortar. And that's a problem because the adhesion properties of the cement mortar will become bad in time. And during earthquakes, there's this risk of the whole parapet wall to be separated from the upper surface of the floor and fall down to over the people walking there. That can cause very bad situations. That's why we can either prefer brick walls, but instead of fixing it directly over the floor, first we can create tiny columns and beams made out of either reinforced concrete or concrete. With this columns and beams, we are creating a sort of frame where we can place our brick wall, and we will be able to fix the whole brick wall, not only at this one line, but at 4 sides. It will be a better way. Or an easier method can be preferring reinforced concrete to create the parapet wall. It can be a 10 centimeter wall for 30 centimeter high or 40 centimeter high, but the whole floor, beam, and parapet wall can be cast at once out of reinforced concrete. That's why our section can be drawn like that. There shouldn't be a line here because we prefer reinforced concrete, the same substance, and we cast them all together. Here, as you can see, the thickness of the floor slab is 10 centimeters. This beam width can be minimum 25 centimeters. The beam height can be proportional with the span, and the thickness of the parapet wall can be only 10 centimeters based on its height. If it's only 30 or 40 centimeters, then the 10 centimeter thickness will be enough. But if you are going to create a higher parapet wall, like 90 centimeters or 1 meter, then you can prefer a slightly thicker wall, like 15 or 20 centimeters, obviously. And over the parapet wall, you need to provide a coping. And based on your building structure, instead of preferring heavy materials like reinforced concrete or bricks, you can create a parapet wall out of thin boards made out of cement, and you can fix them using nails, sorry, or bolts over this system of steel, and you need to have a coping. Here you can see once you do the sloping uh, surface, you can place your water insulation and then heat insulation and so on. But you don't want water to damage the parapet wall. The upper surface of the parapet wall will create a problem. That's why you need coping. Coping, harpusta in Turkish, is like the cap, especially designed and produced cap for the top surface of this parapet wall. And if you like, you can prefer metal sheets, and you can cover this top surface as the coping of this parapet wall. Uh, you can have these metal sheets, but you remember that the metal material, it has this expansion problem due to sun rays heating effect, and you cannot fix it using nails or bolts. If you do that, it will be teared. There won't be any room for it to be expanded. That's why, again, you need to prefer this interlocking method to place the coping over the surface of the parapet wall like this. You can have this long sheet of coping, and you can first fix strips on the surface of the parapet wall like that. These strips, and you can fold the coping into these hook-like ends, and you can place the coping using these hooks like this. You remember that I told you that this roof can be square. And if it's square, then you can prefer same slope. This slope of this surface can be 2%. The slope of this surface can be also 2% because it's square. But what happens if we have a rectangular roof? Not a square roof, but a rectangular roof. Let's take a look. As you can see here, this side of the rectangle is shorter than this side. It's longer. And as you can realize easily, there are two triangular panels like that. They look like they are symmetrical, they are equal. However, their slope needs to be different because this length is shorter than this length here. That means this longer side, let's call it, it's X%. The percentage of the slope is X. It means that this length, for this length with this slope, the whole thickness will be that much. And you need to find the same thickness, but you don't have the same length. You have a shorter length this time on this edge here. That means the slope cannot be the same. It needs to be more than that. If it's 2%, then this slope needs to be 5% or 6% or something. You can easily spot it. With this longer side, this slope is it's not as steep as this one because of the length difference. If you want to have the same slope, let's imagine this is 2%. If you want to do 2% for this piece also, then because of this length difference, the slope, the same slope will not end in the same length, in the same height. It will end in as a higher edge. It will create a higher edge, and there will be this level difference between two pieces. Now it has the same slope, but because the lengths are different, there will be a level difference between these two pieces, and this is something you need to avoid. You cannot cover this level difference with water insulation. There will be problems with the application. That's why when we design a rectangular building, instead of changing the slope or creating a problem like this, we can divide the rectangle into squares or almost squares. Instead of creating a long roof like this, we can divide it into two equal pieces, into two squares, and this part will be directed towards this channel. That part will be directed towards this channel. The water will be collected and transferred with two downspouts. We have one downspout here, another downspout on the other side. We don't see it, but on the top view, we can see it. And the slopes can be equal. Or if we want to collect a whole water at a single point, then again, we can divide it into squares like this. This first part will direct the water towards this valley. The other part will direct the water towards this valley. And the third part will direct the water towards this drainage. If we cannot do it with a single pipe, because it depends on our facade design as well. We don't, maybe there's this window or door where we cannot place the downspout. That will be a problem. Instead of this middle point, we can prefer the corners, two corners. This time we can change the design of the slopes like this. Again, we have two squares, almost squares, or let's say, and this portion will be sloped towards this corner, and that portion will be sloped towards this corner. We can collect the water at one facade, two downspouts at the same facade, or if that will be a problem in terms of facade design, we can collect this square here on this corner and direct the other one towards the opposite corner like that. So the top view will change like this. If we prefer reinforced concrete for the roof structure, and if you are going to place membranes out of either bitumen or plastic, you know that they are very thin. We need to take care of these sharp edges. If we place the membrane directly, then there's this risk of, because it's 4 mm, it can be teared with these sharp edges. That's why first we place leveling concrete for 2 or 3 centimeters. Over that, we apply undercoating or primer base. It's a liquid bitumen, so that once we apply the blowtorch, the liquid bitumen over the surface will melt down. The bitumen of the waterproofing membrane will melt down so that they will be adhered to each other, because the polyethylene film will directly melt down. We apply 2 layers of bitumen sheet, and we can place a separation layer. And for the flat roofs, we need a protection. We can either prefer the same type of leveling concrete, but this time it will be called a protection concrete, protection screed, and the same thing, and the thickness can be again 2 or 2.5 centimeters or 3 centimeters. Or instead of this protection concrete, we can prefer heat insulation for EPS, especially because this will be directly prone to rainwater. And if we prefer glasswool or rockwool, then the heat insulation will be ruined. That's something that we don't want. That's why we can prefer EPS or XPS instead of protection screen. Let's imagine that there is this space underneath this flat roof that produces so much water vapor, like a bathroom or a kitchen. That means the vapor in gas form will travel through the layers of concrete because they are porous, and once they hit the non-porous bitumen membrane, it will cause it to balloon up and be teared uh, like that. We don't want this. So for the flat roofs, we can place these tiny air chimneys that, let's say, I don't know what they are called exactly, but it has this section. We can place these underneath the water insulation, and the water insulation can be we can have a hole on the water insulation so that this towering part can be placed inside this hole. Here you can see the once the excessive gas of water vapor comes here, it can be directed towards this chimney thing, and it will be released like that. And over this, there is this water insulation, so there won't be a water problem, and the gas will be released easily. And for the finishes, we have two alternatives. Let's say three alternatives. The first one is placing gravel over the insulations for 5 centimeter thick. We can place white or grayish gravel, and it will help with the excessive sun rays, excessive heating. If we are going to use this rooftop as a living space, then instead of gravel, we can place a floor covering where we can have our living environment, let's say, like that. Or as a third option, we can have not gravel, not floor covering, but a green roof. Here is this order of layers that you can follow. That's the structure of the building, the floor, the reinforced concrete floor slab. Over that, we have leveling concrete, but with a sloping surface for 2%. And over that, we have a separation layer, 2 layers of bitumen sheet for water insulation. Over that, we have this XPS layer for 5 centimeter and a separation layer and then gravel for 5 centimeters. That's one way to do that. In the second example, we have a roof that we can use as a living space, and now we can have a different layering. Here, the heat insulation is underneath the water insulation, and over the water insulation, we can place the floor covering like that. The third option can be, as I told you, the green roof, where we can place either earth and have these tiny plants. We don't prefer very heavy plants like trees, but grass or maybe flowers, something. And instead of earth, here we can place an artificial plant material here, and above the water insulation, we have spatial layers here. That's the insulations, water and heat insulations. First, we need to put a root barrier. Depending on our plant choices, some of the roots of certain plants have drilling effects, and it can harm the insulations. That's why first we need to prefer wood barrier. It's a special layer, a very strong layer that can prevent that problem of roots. And over that, we can have this drainage mat. As you can see, it has these peaks and grooves uh, like that, and it will help with the rainwater. Let's imagine that it rains so much. There are holes at these peaks of these parts, and all these inner parts will fill with water, and it will reach this level, and it will start to be poured inside these holes, and it will be drained out. The excessive water will be drained out. Uh, so that your plants will not decay because of so much water. But let's imagine that it didn't rain for a while and there's this drought, uh, and you don't want your plants to die. Uh, and these holes, these middle parts, will hold the water for a certain period of time, where your plants can get all this water here. It's good for that. And in between, we can place a filter layer because over that, either we place earth, and we don't want the earth to clog these holes or cause problems, or we can place plant nutrient layer. It's an artificial earth, let's say, where we can have tiny plants. But you should keep in mind that this system is pretty heavy, and the thicknesses, it's important. You don't want very thick layers over your floor, and you need during their weights, you may need to enhance the structural capabilities of your floor and your building structure as well. Okay, thanks for listening. That's the end of the rules. Hopefully next time we are going to do the walls.